Hi, this is lesson 1 of Unit 5. Unit 5 deals with reaction rates. In this lesson, we'll be talking about the following topics. We're going to talk about all the factors that affect our reaction rate, whether it goes fast or slow. We're also going to get into calculating the reaction rate as well. So for our lesson objectives, students will learn how temperature, pressure, and concentration affect how fast a reaction goes, as well as all the calculations needed to figure out the rate of a reaction at a particular spot in time. So we're going to begin our conversation with factors affecting reaction rates. What are all the things that affect the reaction rate? To begin our conversation, though, we have to understand what is a reaction rate. The definition for a reaction rate is the rate of disappearance of a reactant or the rate of appearance of a product. That's a definition, right? So let's talk a little bit more about it. In a chemical reaction, your reactants is what you start with. Your product is what you finish with. As time goes on, there's going to be less and less reactants, and those are seen in the graph on the slide by the red line, and you see how it's decreasing over time. And so what that reactants, they're turning into the products. So there's going to be more and more products. In the graph on the slide, you see that's represented by the blue line, where you start with 0 at the very beginning, and it's going to go ahead and climb up. Now, the graph right there is very characteristic in the sense that initially, in the very few first seconds, it has a very steep slope. The reactions begin very quickly, but then over time they tend to slow down. So one more time, the reaction rate is how quickly you use up the reactants or how quickly you make the product. So that is reaction rate. Now, collision theory states that atoms must collide in order for a reaction to take place. If you have two atoms, they actually need to collide with each other, otherwise they will not react. If you have more collisions, that's going to lead to a faster reaction rate. So that's really what you want. You want more collisions, that will give you more reactions, a quicker reaction rate. For activation energy tells you how much energy you need to supply so that a reaction can take place. So for example, if you think of a substance that's very volatile, like alcohol only needs a very small spark to catch fire. So that alcohol would have a very small activation energy. On the other hand, let's say you have a big giant block of wood and you want it to go ahead and get it to catch fire. Well, you're going to go ahead and need to get it very, very hot, put a very hot flame up to it so it can eventually will catch fire. Once it catches fire, that reaction will keep going, but it's going to need a lot more energy than it is if you had, let's say, a cup filled with alcohol. Again, one spark could get that to catch fire. So that's the activation energy, the energy you need to get that reaction going. So if it has a very large activation energy, that reaction tends to be very small. All right, so a substance with a large activation energy will have a very slow reaction rate because it takes a long time to supply with that energy before the reaction gets going. On the other hand, if you have a substance with a small activation energy, it will tend to be very fast. In the pictures you see right there, we have our giant log of wood. Again, to get that to burn, you're going to need a lot of heat and a lot of time to get it hot enough so it catches fire on its own. So that will have a very large activation energy, so it'll tend to go very slow. On the middle picture, you have some isopropyl alcohol right here, and that's going to go ahead and have a very small activation energy. Like I said, a spark is enough to get that reaction going. If we were to go ahead and do a graph for the small activation energy versus a large activation energy, you would see it right here where the alcohol would represent this red line with a very small activation energy right here. So therefore, it's a very quick reaction. You can easily go from reactant to product in a short amount of time. The log, being so big, has a very large activation energy. That will be represented by this black line, and you see how much energy you have to put in before you can go ahead and start turning the reactant into product. So the size of the activation energy will affect how fast or how slow that reaction will take place. Another factor that will affect how quickly a reaction happens is the concentration. Remember, we talked about collision theory. The molecules need to collide with each other before a reaction takes place. Now, if you look at the slide at the bottom, let's pretend that this red molecule on the left wants to collide with these blue molecules, but there's only a few. How long would it take before they collide? It might take a few seconds. But on the picture on the right, the red molecule needs to collide with one of the blue molecules. but there's a lot more blue. There's a higher concentration, so therefore the chances of collision are much higher. It's going to happen a lot quicker. So in concentration, says the number of particles in a volume, that's concentration. A substance with a high concentration, like the picture right here on the right, will have a fast reaction rate because there's going to be a lot more collisions, so those collisions will happen in a shorter amount of time. A substance with a low concentration, like the picture on the left, will lead to a slower reaction rate because now you have less collisions, so those collisions will take longer to take place. So that's how concentration affects how quickly a reaction takes place. For temperature, an increase in temperature will increase the speed of the molecules. So these particles are going to move a lot faster. If you heat them up, the atoms, the molecules are going to move faster. If they move faster, they're going to collide more often. And again, more collisions means a faster reaction rate. So fast-moving particles will collide more often, leading to a fast reaction rate. If you heat up a substance, it's going to react a lot quicker. On the other hand, if you cool down a reaction so it's at a lower temperature, that's going to go ahead and have the molecules moving slower. Slower molecules means less collisions, and less collisions, that means a slower reaction rate. So that's how temperature affects the rate of a reaction. Now, gases. In gases, an increase in pressure by reducing the volume will increase the number of collisions. So if you look at the picture, so we have these gas molecules moving around, but now let's go ahead and bring down this piston. Notice how it's further down. So we decrease the volume. Now that's going to move the molecules closer to each other. So therefore, that's going to increase the number of collisions. So the increased number of collisions will lead to a faster reaction rate. And vice versa. What if we expand the volume? That's going to separate the molecules further away from each other. So therefore, there'll be less collisions, and therefore they will have a slower reaction rate. The second bullet on the slide states that solids and liquids are not affected by pressure since they're not really compressed. Only gases are affected by pressure. Now, surface area plays another role. Here we have the block of wood again. Here, so we have our log. And what if we were to go ahead and chip it away and we have just, oops, pardon me, wood chips right there? And says a substance with a high surface area will react much faster. The wood chips on the right are going to go ahead and have a much, much higher surface area. Why is that important? Now, oxygen, which is needed to combust all those wood chips to get them to burn, now oxygen can easily access all parts of the wood when compared to a log, where we can only access of the very small surface area of that log. So if you have a very high surface area, like the wood chips on the right, that reaction is going to go much, much faster than the log on the left, with a very low surface area. It's going to take a lot longer to get it to catch fire. Now, other things that will affect how quickly a reaction takes place is the binding site. The binding site is where the reaction takes place. If you have two molecules collide, for some molecules, it must happen in a particular part of the molecule. If the binding site is very exposed, so that means that it's easily accessible, like the molecule on the right, then it's very easy for another molecule to collide to access that binding site. So those reactions tend to be faster. But if the binding site, like the molecule on the left, is more cluttered, is more difficult to access, then that molecule will have a slower reaction rate because other molecules cannot access it or have trouble accessing it. It's going to take longer for a collision to take place at the binding site. That's going to slow down the reaction. So the more exposed binding site is going to go faster. The more cluttered, the more the binding site is hidden by other parts of the molecule. That's going to slow down the molecule. Here, the binding site is represented by that red atom. Now, another thing that will affect how quickly a reaction will take place is the presence of a catalyst, a substance that speeds up a chemical reaction by lowering the activation energy. That is known as a catalyst. Now, the catalyst does not itself get used up in a chemical reaction, so it could keep on catalyzing reactions over and over and over without itself being used up. So a catalyzed reaction will lower the activation energy. Less activation energy means a faster reaction rate. On the other hand, an uncatalyzed reaction might have a very high activation energy. High activation energy means that it's going to have a very, very slow reaction rate. So those are all the things that affect how quickly a reaction takes place. Now, What's the opposite of a catalyst? Well, that will be an inhibitor. An inhibitor is a substance that either stops or slows a chemical reaction. Now, how does it work? Well, picture this molecule, right? That's actually a virus right there on the left-hand side. It's a virus. And what the inhibitor will do is to attach itself to a part of the virus. Here I have it going all the way around it, but in reality, I just go after a particular part, the binding site, and it will attach itself to it, and it will not allow the reaction to take place. A lot of times, sometimes I explain it this way to students. Picture you have a key, and you're going to go ahead and put it into the lock on a door. All right, so that's the chemical reaction. The chemical reaction is going to unlock the door. All right, what if someone were to go ahead and put some gum onto where the key goes? All right, so therefore the key can no longer access the lock. You cannot unlock the door. So that's a good example of how an inhibitor might act with a virus, such as the one you see right there on the slide. It's going to go ahead and attach to it in a particular spot, block it. Although the lock's still there and it is intact, it is blocked. The binding site where the key enters, it is blocked, so it does not work anymore. All right, now let's go ahead and change topics a little bit. We're going to go ahead and talk about rate calculations. How do you calculate how fast a chemical reaction goes? Now, right there it says reaction rate is the rate of disappearance of a reactant. We have mentioned that earlier, or the rate of appearance of a product. So rate is how quickly it goes, right? Now, if you're driving down the street, your rate at which you're going down the street is the speed. Perhaps you're going at 25 miles per hour in a residential area, maybe 65 miles per hour on a freeway. But the miles per hour, that is how you measure the rate. Miles is your distance over time. What about for a chemical reaction? That's going to be the molarity per second. That's usually the unit used to measure that. So if you're measuring how quickly a reactant is disappearing, so that'll be the top form is going to be the final concentration of the reactant. Here they have it as RF, so that's the final concentration of the reactant, subtracted minus the initial concentration of the reactant. So what you finish with minus what you started with, over time final minus time initial. For the product, it's going to be very similar. We have the final product minus the initial product divided by the final time minus the initial time. And that's what's going to go ahead and give you the concentration of the reactant. It's going to be in molarity per second. Now, if you look at both of those formulas, aside from the fact that the numerator, on one we have reactant and the other we have a product, there's also the fact that we have here a negative for the reactant. The reason why we have the negative for the reactant, if you could go back a slide, you'll notice that the red line, which is for the reactant, has a negative slope. So we add another negative, so therefore our rate will give us positive. So whether we're looking for the reactant or the product, we always want a positive answer. So that negative is added to the reactant to counteract that negative slope for the reactant. The blue line is the product, is a positive slide. So our answer is already positive, which is why you don't see the negative for the product, only for the reactant. Now, in example 1, we're asked the following question. Calculate the reaction rate between the following time intervals, between 0 and 5 seconds, 5 and 10, and so on, all the way down to 30 seconds for a reaction. Now, the data required for these calculations in the previous slide, so let's go ahead and take a look at it. So here we have, there's a table, and there's 7 data readings right there for our made-up reaction of A, B, decomposing into parts A and B. So here's the concentration of the reactant, AB, in moles over liters or molarity, and the time intervals at which each of the readings were taken. All right, so now let's go ahead and find the reaction rate between the first time intervals, 0 and 5. All right, so what you would do then is you would get the concentration of the substance, the second one minus the first, because it is final minus initial, and then you would go ahead and divide it by the time, again, final minus initial. So we'll be looking at lines 1 and 2, because that's where 0 and 5 are. That's the time interval we're looking at. So it'll look like this. Reaction rate, it's equal to negative, because that is a reactant, so its slope is negative. So, but we want the answer to be positive. That's why we add the extra negative. So it's going to be 0.29 minus 0.5 over
the time interval, 5 minus 0, that's in seconds. Stop point is in molarity. So let's go ahead and get the calculator. 0.29 minus 0.5. We end up with 0.21 over 5. So we divide. We end up with 0.042 m over s. That is the reaction rate. That's how quickly this reaction is taking place between time interval 1 and 2. Next, from 5 to 10, so I'll be between time interval 2 and 3, so between 5 and 10 seconds, what is the reaction rate there? Most reactions, they start very quick and then begin to slow down. So my expectation is to have a smaller number than the 0.042 that we got for our first time interval. So let's go ahead and plug in the values. All right, again, it's final minus initial. So it's going to look like this. Reaction rate is equal to 0.20 minus 0.29 over 10 seconds minus 5 seconds. That gives us 5 seconds in the denominator. On the top, 0.09. So 0.09 divided by 5 is going to give us 0.018 m over s. Notice how the reaction began very quickly, but now it's slowing down. And it's going to go ahead and continue to slow down. The rate is not nearly as large as the original. And as we keep going, you're going to see that number drop and drop and drop. Eventually, once you reach this equilibrium, the slope of the line will be flat, so therefore you have a 0 reaction rate. All right, let's continue to the next one. Letter C, between 10 and 15. So we'll be looking at trial 3 and 4 of the data. So it'll look like this. So reaction rate is equal to negative to 3 and 4, 0.14 minus 0.20 over 15 minus 10, and that's in seconds. So we end up with 5. Every 5 seconds they get the time interval. That's why you always see a 5. And that's going to be 0.06. So 0.06 divided by 5 is going to go ahead and give us 0.012 m over s. So yeah, as expected, the concentration keeps dropping. Let's go ahead and continue between 15 and 20 seconds. What happens there? Plug them in for the reaction rate. It's going to be 0.10 minus 0.14 over 20 minus 15. So it's going to give us 5 seconds for the denominator and 0.04 in the numerator, and that is 0.04 divided by 5, 0.008 m over s. All right, let's continue to the last two, between 20 and 25 seconds. So we'll be looking at 5 and 6 right here. So it's going to be reaction rate is equal to negative 0.07 minus 0.10 over 25 minus 20. So this gives us 5 seconds in the denominator. And 0.07 minus 0.1 divided by 5. This is 0.03 divided by 5 gives me 0.006 m over s. And finally, last one, between 25 and 30 seconds. So we'll be looking at trials 6 and 7. And we'll go ahead and plug in our values. It's going to be reaction rate. It's equal to 0.06 minus 0.07 and 30 minus 25. So it's going to give us 5 in the denominator and 0.01 there. So it's going to be 0.01 divided by 5. We end up with 0.002 m over s. So you can see how the reaction rate keeps dropping. The reaction as it continues is going to get slower and slower and slower. That takes care of example number 1. In example 2, we're asked the following question. Graph the data on table 1, then answer questions A, B, C, D. Alright, so let's take a look at the data. And here's our data. We're going to go ahead and graph it. We have here on the y-axis, we have the concentration in moles per liter. And on the x-axis, we have time measured in seconds. So we're going to go ahead and plug in the values. Alright, so the first data point will be at 0. It is 0.5. So here's time 0. It is 0.5. So there's our first data point. At 5 seconds is 0.29. So we're going to go ahead and put it right around here. Alright, next at 10 seconds is going to be 0.20. At 15 seconds is going to be 14. So we're going to be somewhere around here. At 20 seconds is going to be 0.10. And 25 is going to be 0.7, somewhere around here, and finally at 30 is going to be 0.6. So more or less that's what we got. What's next for us? We're going to go ahead and draw a best fit line that's going to go ahead and try to touch as many of these points as possible as we draw the line, and as smooth as possible. Alright, there we have it. Alright, not bad. Did miss a couple points, but pretty close. Alright, so it is a curved line, and notice that, yeah, we have a very steep slope at the beginning because reactions started very slow, but as we get closer to the end, the reactions begin to slow down, and now we have a very shallow slope. Alright, now that we have the graph, we can go ahead and go back to the questions A, B, C, and D in example 2, and go ahead and answer those as well. So in part A, they ask you, what is the concentration at 8 seconds? Alright, so we're going to use the graph to figure that out. So part A, you want to know what is the concentration of AB at a time interval of 8 seconds. Alright, so we're going to go ahead and solve for that. So we go to the graph, here's 0, 5, 10, so 8 seconds somewhere around here. Alright, so at that time interval what we do is go up, straight up, and then over to the side. That's somewhere around 0.21. That'll be my concentration in moles per liter. Alright, so that's our concentration. So this will be our answer for part A. Part B, they ask you, at what time will the concentration drop to 0.15 molar? So they're going to give you the concentration, ask you, well, how much time would that take? Alright, so 0.15 molar, here's 10, there's 20, 0.15 smack in the middle, so you just go across, where it hits the line, you go straight down. Now I would say that would take somewhere around, that's 10, that's 15, about 13 seconds. So that would be my answer for part B, approximately. In question C, they ask you, what is the concentration at 23 seconds? So 23 seconds, here's 20, 25, 23 will be somewhere around here. So you go up from 23, where it hits the line, then you go across. And I would say so that's somewhere around 0.8. So 0.08 I meant. Alright, that's at 23 seconds. That will be that concentration, 0.08 moles per liter. And finally, letter D. He asks you, at what time will the concentration drop to 0.25? So let's go to 0.25, between 0.20 and 0.30. So there's 0.25. Then where it hits the line, it goes straight down. Now I would say that's somewhere around 6 seconds for the answer. That's when we have a concentration of 0.15, 0.25 molar. So the answer will be 6 seconds. So there are your answers for A, B, C, D. That takes care of example 2. In example 3, we're asked the following question. The activation energy for an exothermic reaction is 20 kilojoules and has a total energy change of -5 kilojoules. Alright, it's an exothermic reaction. That means that it's going to release more energy that was put into it. So let's go ahead and start the graph for that. Then we'll read to the final question. So we're given an energy diagram. So energy is on the y-axis and time here. So it'll be energy, time. And we're going to go ahead and start with our reactant. We're going to put it here, so R. Now the activation energy for this reactant is given to us. It is 20 kilojoules. So I'm going to make it 20 high. So that is our height. So from this point to the top, it's going to be 20 kilojoules of energy. Next, they ask us the total energy change is -5 kilojoules. That means that it released 5 kilojoules. Now it's exothermic. That means that this line where the product is going to be lower than the reactant. How much lower? By 5 kilojoules. It's negative. That means it's 5 below the reactant. Alright, so I'm going to go ahead and draw that line. So here's our product, and it is 5 below the reactant. To that line right there, 5 kilojoules. Negative is because it's below the reactant. Alright, here's the question that they want us to answer. Now that we've drawn this, what is the activation energy for the reverse reaction? Which means, how much would you have to climb from here to get all the way to the top there. Alright, so again, this is our 0 point, that is 5 below 0. So the answer for this would be 5 from here to there. From here to there is 5, and from there to there is 20. So the answer for this question would be 25 kilojoules of energy. So that is the answer for this problem. The activation energy, EA, equals 25 kilojoules, because you have to climb the first 5 from here to there, and then another 20, so altogether 25 kilojoules for the reverse reaction going from product over to reactant. That takes care of example 3. Let's go ahead and take a look at now at example 4. In this one, we have an endothermic reaction. What that means is that you're going to put more energy in than what you're going to go ahead and get out. So how will this graph change? Alright, we're going to still begin with the reactant here, but now the product's going to finish above it. So somewhere over here. We'll get to it in a second. It says the activation energy for the endothermic reaction is 30 kilojoules. So I'm going to go ahead and draw the line from here, slightly higher than the previous one, because it said it was 30 kilojoules. So from here to there, it went up 30 kilojoules. Next, what happens after that? It says, and the total energy change is 12. Alright, so that means that for wherever the reactant is, which is essentially 0, it's going to go ahead and gain 12, so it's going to be 12 higher. So that's where the product is at. So it's going to be, from this line, 12 kilojoules. We're going to continue the line, drop down to there. So that's where it is. Now the question again, what is the activation energy for the reverse reaction? So from this point all the way to the top, what you would do here is, we're starting at 12, and to get to the top here, it's going to be, what's the difference between 30 minus 12? So the answer for this one is 18. So our activation energy for this endothermic reaction is 18 joules. That will be activation energy for the reverse reaction, because it will be essentially 30 minus 12, and that's how we get our answer of 18 kilojoules. That takes care of example 4.